All right, this is section 4.4 in calculus, and this is the big one. This is the very first day of it, of about 2 weeks. So this is just going to be a little bit of an intro, a little bit of the kind of the algebra or the mechanics behind it, and then we'll get into much more of the understanding in the next 2 weeks. So, first of all, the fundamental theorem of calculus states that uh, differentiation, how about if I say that derivatives, okay, it says that derivatives and integrals are inverse operations. Okay, inverse operations. Now, don't be confused by when we say inverse operations. That doesn't mean they are reciprocals of each other. It doesn't mean that they are opposite. Inverse operations means it's something that it means they undo each other. For example, if I had, let's say, an x squared, in order to undo the square, in order to get rid of the square, I would have to take the square root. So a square root and a square are inverse operations. Or I could say, if you're solving an equation, let's say, 2x equals 10, in order to solve, you would divide by 2. That's because right now it's 2 times x, and the inverse operation of multiplication is division. So dividing will undo the multiplication. Okay, so that's what we mean when we say inverse operations. So derivatives and integrals will undo each other. So let me see if I can give you just a basic explanation related to the concept. So we have said differentiation represents, in other words, derivatives represent, if I had to give it one word, I would say slope. Okay? Derivative and slope. And I went on to say, it's the slope of a tangent line, but it's in general, it's slope. Slope of a curve, slope of a tangent line, just slope. And think about it. Back in the day in Algebra 1, when you first learned about slope, the whole, you said it was the change in y over change in x. So I'm going to write it as delta y over delta x, right? That's like saying y2 minus y1 over x2 minus x1. Integration, like we just talked about the other day, represents area under a curve. And you may think, oh, slope and area don't undo each other. Well, that's true, but let's look at the concept. Let's look at what's actually happening. Where slope was change in y over change in x, remember area, what we were doing was we were adding up a whole bunch of areas, right? And let's say area of a rectangle. In order to find, let's just do this, whenever I had whatever curve, in order to find the area of this rectangle, I did the base, which was this distance, times the height, which was this distance. Well, would you agree that the base right here is the difference in this x value and this x value, right? So wouldn't that be like saying the change in x? And the height, which is this distance, would be like this y value minus this y value. Well, wouldn't that be the change in y? So to find, which we're saying is the height, so to find the area of a rectangle, you're doing the change in x, which is the base, times the change in y, which is the height. Well, look at that. That's kind of a very basic example of inverse operations. You have you have division up here for slope, where you have multiplication down here for area. And it's division and multiplication of the same two values, change in y and change in x. Okay, so that may mean very little to you, but here's how we will actually do the mechanics, the algebra, the analysis of integration as far as the fundamental theorem of calculus. So I shouldn't have written this piece right here. It's going to be confusing. Just look at the integral that we have there. So we've talked about a definite integral, right? And we said, it's kind of like you're integrating the derivative. And we said when you integrate the derivative, it takes you back to the original function. That's what we did when we first learned integration. But now that we have boundaries, what we're going to say is we have to evaluate that from A to B. And what that means is when you evaluate it from A to B, that means first you plug in the B, and then you subtract what you get when you plug in the a. So that's what the fundamental theorem of calculus says. And I get right now that's a little bit underwhelming. All I'm telling you what to do is how to go from the integration that we did a week ago to adding that a and b boundaries. So here's how it works. Number one, integral from 1 to 9 of square root of x. All right, forget the 1 to 9 for just a minute. Let's do the integration of square root of x. Now we're going to think of this as x to the 1/2, right? So if I integrate x to the 1/2, it's going to be x to the n plus 1 over n plus 1. And instead of saying over 3/2, I'm going to say times 2/3. Okay, so now instead of writing plus c, which is what I would have normally done, instead of writing plus c, I'm going to say I'm going to evaluate that from 1 to 9. Okay, so what that means is first plug in the 9. So I'm going to have 2/3 times 9 to the 3/2 minus, now plug in the 1 where I have 2/3 times 1 to the 3/2. Now, mind you, I'm kind of writing out every step on this one. I realize you could skip to some simplifying, but just to kind of show you every single step. So now let's do the math. I'm going to have 2/3. Well, what does it mean to have 9 to the 3/2? Well, remember the denominator tells you the root. So the square root of 9 is 3. And then the numerator tells you the exponent. So 3 cubed is 27 minus 2/3. And 1 to any power is always just 1. So that's 2/3 times 1. And so if I want to actually simplify this, and by the way, these are usually multiple choice questions, so you will have to simplify it, unlike a free response, where you don't have to simplify. So if I simplify, let's see, 3 goes into 27 9 times. So I actually have 18 minus 2/3, which is going to come out to be 17 1/3. Okay? Now, what does that mean? Well, that means since integrals represent area, if I were to imagine the graph of that square root of x, which is something like this, and if I were to mark off the area from 1 to 9, then the area under that curve between 1 and 9, the exact area is 17 1/3. It's not an approximation. That's the exact area. Okay? Number 2, if I were to integrate cosine, I know that's going to take me back to sine, just positive sine. And if I evaluate that from 0 to pi, then I would say, well, the sine of pi is 0, and the sine of 0 is 0. So that means the whole thing equals 0. All right, so that's my answer. The integral equals 0. Does that mean there was no area? No, what that means is the amount of area above the x-axis was equal to the amount of area below the x-axis, and the positive and negative canceled out and gave me 0. Again, we could show you the picture of it. Think about the cosine. Cosine is the one that starts up here at 1, right? Comes down through and then back. Well, here's where x equals 0. Here's where x equals pi, and that's exactly what happened, right? This amount of area, if I had drawn this nice and accurate, is the same as this amount of area, but because integration was looking at this as being a positive and this as being a negative, and so that's why it canceled out to be 0. But the integral actually equals 0. If I said how much area is represented, well, then I would have to just integrate this piece, see what I get, and then double it in order to account for this piece. Okay, but the integral is 0. All right, so look at example 3. So the big part of today is going to be just remembering how to do all the integration. All right, let's try this one. So remember we said I can't integrate this as is, but what I could do is I could separate these terms. So what I really have here is the integral from 1 to 3. X squared over x is x, plus 3x over x is 3. So really, this is what I'm going to integrate. And if I integrate x, I'm going to get x squared over 2. And if I integrate 3, I'm going to get 3x. And if I evaluate that from 1 to 3, Let's see. First, I plug in the 3, so 9 halves plus 9. So all of that is plugging in the 3 minus, then I plug in the 1, so 1 half plus 3. And then let's just do the simplification. Let's see. I'm going to think of this as 9 halves plus 9 minus 1 half minus 3, just because I think it's easier to kind of simplify the math in my head. 9 minus 3 is 6. 9 halves minus 1 half is 8 halves, which is 4. And if I put those together, I'm going to get 10. Okay. Now, let's look at example 4 real quick. If you look at it, you can't integrate it as is. Do you see that this is going to be one where you would have to do a U substitution? Okay, so if this is actually class that I'm teaching this, what I would do at that point is I would stop and I'd say, okay, hold off on the U substitution. I'd say go over and try the homework, like at least the, let's see here. Really, you can try the whole first page of homework. It's not even until the last few problems that you get to the ones that require U substitution, okay? But it's not. I'm not going to sit and wait for you to do those homework problems. So how do I handle this when there's U substitution? Well, here's what we're going to do. Start off by doing the U substitution just exactly like we would. The parenthesis is this one. So U is x squared minus 3. Remember, you always do U, du, and dx. So du is going to be 2x dx. And then if I solve for dx, I'm going to have du over 2x. And hopefully at this point, you're getting pretty good at seeing what's going to cancel and everything. I mean, can you tell right now that 2x is going to cancel that 2x? So when I rewrite this, I'm going to have the integral. Now I'm going to hold off on the 1 and 2. I don't want to write those down yet. And I'm going to, instead of parenthesis cubed, I'm going to say u cubed. And then in place of, oh, look at that, I have a bad notation thing here. There should have been a dx. Because then I can say, in place of the dx, I'm going to put du, because the 2x already canceled. Now, let's talk about that 1 and 2. If you bring that 1 and 2 over as is, it's incorrect notation. Why? Because the variable is u, but the boundaries, the 1 and 2, are in terms of x. Those are x numbers, okay? And just like when we said you don't want to have x's and u's both in the integral, you also don't want to have x boundaries with u variables. So what does that mean? Well, that means I either need to be all x variables and x boundaries, or I need to be all u variables and u boundaries. Well, so you might be saying to yourself, how do I get u boundaries? Well, look right here. This is the definition of u. If x is 1, then wouldn't u be 1 squared minus 3, which is negative 2? And if x is 2, wouldn't u be 2 squared minus 3, 4 minus 3, which is 1? Now, this is proper notation because I have u variables and u boundaries. Okay, so now finish it out. Let's do the integration. If I integrate u cubed, I'm going to get u to the 4th over 4. I'm going to evaluate it from negative 2 to 1 because once you change it to u boundaries, you don't have to go back to x. You can just finish it out like this. So if I plug in the 1, I'm going to have 1/4 minus, if I plug in negative 2 to the 4th is going to be positive 16 over 4. So 1/4 minus 4 is going to be 3 3/4. Okay. So the key takeaway here is that you have to have u boundaries with u variable. Now, there's a couple of problems, again, over here that if we're in class, I would say, okay, now go try, I would say 71, 73, and 75, doing u substitution the way we talked about it. But I want to show you how they tend to ask this as a multiple choice question. And I know this wasn't originally in the notes, so you don't want to ignore this. This is an important question. So this is what a u substitution might look for in multiple choice. It says, using the u substitution, u equals the square root of x minus 2, this integral is equivalent to. Okay, so two things I want to talk about. Notice all of the answer choices are integrals. So a lot of times you don't actually have to do the integration. You just have to rewrite it in terms of u. And the other thing is, on this type, they'll always tell you what to use for the u substitution. It might be what you would have chosen, and it might not be what you would have chosen. It doesn't matter. Whatever they say to use for U substitution on multiple choice, that's what you have to use. Okay, so let's go through the process. If I let U equal, I'm going to write x to the 1/2 minus 2, then go through the du and the dx. So du would be 1/2 x to the negative 1/2 dx. And you know what I'm going to do before I solve that? It's just easier for me when I solve for dx. I'm going to think of the du. I'm going to move that x to the negative 1/2 down. I'm going to think of it as 1 over 2x to the 1/2 dx. Because now when I solve for dx, do you see that really I'm just multiplying by the du? So 2x to the 1/2 times du. Okay, so when I rewrite this integral, forget the 1 and 9 for a minute. Forget the 2 for now. The denominator is the u. In place of this dx, I'm going to put 2 times x to the 1/2 du. Okay, so there's a couple things I have to take care of here. First of all, I don't want u's and x's. And notice all the answer choices are u's. So I need to get rid of this x to the 1/2 right here. Well, let's see, that's x to the 1/2. What could I put in place of x to the 1/2? Well, look at this. Wouldn't x to the 1/2 be u plus 2? So what I could do is, in place of this, I have u plus 2. The 2 times 2, this 2 and this 2, is just a 4. And it's still over u. Okay, so now I'm all in terms of u. Now the only thing I have to worry about are the boundaries. Well, since I have u variables, I can't use x boundaries. In fact, on these kind of multiple choices, you could immediately say, well, hey, look, since the x boundaries are 1 and 9, you could immediately say it can't be that, and it can't be that, because they have u variables with x boundaries. Okay, so I'm assuming, because of looking at the answer choices, that when I change it to u boundaries, it's going to be negative 1 and 1. I mean, I doubt that it's going to be none of these, but let's do a quick check. So how do we find the new boundaries? Well, I plug in. If x is 1, then u is going to be square root of 1 minus 2 is negative 1. And if x is 9, u is going to be 3 minus 2 is positive 1. So, yep, that sure is it. And do you see? It looks like that's the one that fits. So that's a lot of times what the multiple choice would look like, which is, it's good because it saves you the work of having to do the integration. You just have to rewrite it in terms of u. Okay, so that is 4.4.